Alright, so we just discussed the long-term behavior of polynomials, but we'd also like to discuss what happens between positive and negative infinity. How do these polynomials behave? And to kind of help illustrate that idea, we're going to take a look at what happens with quadratics, first of all, since those are the most recently studied types of polynomials, and we'll extend those ideas to polynomials in general. So over here, I have the graph of the polynomial x minus 3 times x plus 1. And we know that this thing has the shape of a quadratic, and specifically the parabola x squared minus 2x minus 3. And since it is a polynomial of degree 2, its shape is a parabola. Because it has a positive leading coefficient, it's curved upwards like this. And in particular, it's 0 at -1 and at 3. And you might be able to recognize this from the factorization here. The fact that x squared minus 2x minus 3 is equal to x minus 3 times x plus 1. Now, something that gets kind of buried in a lot of this discussion in most textbooks, I find, is why this factorization actually yields the zeros of a quadratic or a polynomial or what have you. And the reason for that is, in order for this term to be zero, since this and that are the same thing, in order for this to be zero, this must be zero. And this is 0 if and only if one of these two things is 0, x minus 3 or x plus 1. If either one of them are 0, then when I multiply them together, the whole thing is 0. If both of them are not 0, then when I multiply them together, whatever I get, it's not going to be 0. So I can identify when this is 0 by figuring out when each one of these factors is 0. And there's 0 when x is 3, 3 minus 3 is 0, or when x is -1, -1 plus 1 is 0. So that's exactly what we get here. If I turn that off and I turn that on, you see that I get the exact same problem. And of course, we know we could mess with this by flipping it over and stuff like that. But this is one of the ways that you can have a 0 in your polynomial. Is we have something that goes from positive to negative and from negative to positive. Now note that in order to have a function that has a 0, there are basically two options. You can cross the axis here and then cross again here, or you could bounce off of the axis. So for example, if instead of x minus 3 times x plus 1 add x minus 3 squared, then at 3 it just bounces off the axis. And the reason in this case that it bounces is this x minus 3 squared term here, it doesn't change sign, right? X minus 3 is always positive or 0 when you square it. So it's 0 when x is 3, and otherwise it's going to be positive. So let me kill that. If I do something like multiply that by x minus 1, say, then at 1, this thing crosses, and at 3, it's going to bounce. Why? Because x minus 1 to the first is an odd degree power, so this thing is allowed to change sign. It's allowed to go from negative to positive, because x minus 1 to the first can change signs. But when I hit the 3, the x minus 3 squared does not change signs, right? It's always non-negative, so it's forced to stay on the same side. Now if I were to change that to a cube, we would find that it crosses both here and here since they're both odd powers. Or if I were to turn this thing into a squared, then it would have to bounce both here and here. But if I were to throw another x to the cube next to it, then it would cross at the 0, bounce at the 1, bounce at the 3. So the general rule of thumb is that you bounce when you have even degree powers and you cross when you have odd degree powers. And then the long-term behavior is the same as x to the 7th, because if I multiply the leading terms of this thing, I'm going to get x to the 7th plus a bunch of garbage that gets eaten as x's values get big or small. So just knowing that, even if I didn't have this technology available to me, I know that this thing is an odd degree polynomial, so it goes from negative infinity, goes to 0, crosses, bounces, and then bounces again, crosses at 0, bounces at 1, bounces at 3. So remember, the key thing again is cross when odd, bounce when even.